Computer, what is machine functionalism? Define it for me.
Here's something I found from the article Functionalism, Philosophy of Mind on Wikipedia. According to machine state functionalism, the nature of a mental state is just like the nature of the Turing machine states described above.
Yeah, okay, so almost there. Hopefully we'll get her to help us out today in figuring out what functionalism is, and specifically what machine functionalism is as a theory of mentality. As the philosopher Ned Block puts it, functionalism is a family of views. It's not just a single view. It's a family of views motivated by different concerns that have a family resemblance in terms of how they define mental states. Functionalists understand mental states as functional states, something that you can define in terms of a set of input conditions and a set of output conditions, and each functional state is a particular set of that input and output relation. So you can define any mental state, according to functionalists, as a relationship between inputs to the system or stimuli into the system and outputs away from the system. And different forms of functionalism disagree about what those inputs and outputs look like, what kind of work that they do, how we specify the inputs and the outputs, and what it is that essentially defines what makes one mental state type identical to another mental state type, and what it takes to fulfill a functional role, what it takes for something to actually instantiate those input-output relations. So one kind of functionalism that we're going to talk about today is called type identity functionalism. According to type identity functionalism, what Ned Block calls psychofunctionalism, each mental state is identical to a functional state. Or put another way, each mental property is identical to a functional property. Mental states are dispositions to act in certain ways and have certain mental states, given sensory inputs and certain mental states as inputs. So philosophers like Putnam, Fodor, and Harman have views like this. For example, for the philosopher Hilary Putnam, in an article he wrote in the 60s, pain is a mental state type that can be defined as identical to the functional state type defined by the relations between inputs like tissue damage and outputs like wincing, crying out, avoidance behavior. So basically, people like Putnam are saying that we can define mental states like pain. Maybe we understand them first personally like experiential states, pain is ouch, right? But for people like Putnam, you can define the mental state type pain by reference to the things that cause it and the things that it itself causes. So in this case, the things that cause it are the stimulus, the inputs, things like tissue damage, and the things that it causes then are stuff like wincing, crying out, avoidance behavior. And for these types of functionalists, you can also often embed mental state types as taking other mental states as inputs or outputs. So maybe, the pain state also has a tendency to output behavioral stuff and belief states, for example. So like maybe the mental state type has a disposition to produce belief states, and that would be part of its functionally specified profile. So this type identity functionalism, you can compare to the view we were studying much earlier, which is called mind-brain identity theory. According to mind-brain identity theory, the mental state type is identical to a physical type. So the mental states, according to mind-brain identity theory, are identical to brain states. Now, the functionalist is disagreeing with the mind-brain identity theorist in the sense that they think that the type of mental state is actually identical to a type of functional state. So the brain isn't necessary for instantiating a functional state, depending on what functional state it is you're talking about and how specific you get with the specification of that functional state. So broadly speaking, functionalism is a family of views that accepts what we call multiple realizability. That means it thinks that different types of things, things made of different types of stuff, can all have mental states. Because note, right, functions aren't the kinds of things that require a particular material specification. I can build an electric can opener or a hand-powered can opener, and both will be equally good can openers because both fulfill the function of being a can opener. Similarly, functionalists think that minds are things that you could potentially build out of multiple types of materials, not just brains, but maybe also silicon chips or electric circuits, right? And other things. Maybe you can make a mind out of cheese, I don't know. It depends on whether or not cheese can fulfill the requisite functional profile for what you think minds have. Now, one more specific form of functionalism that has been popular for a few years, and out of which was birthed the very beginnings of cognitive science, is a kind of functionalism called computational functionalism, or sometimes it's called machine functionalism. The slogan of the computational functionalist is that the mind is the software of the brain. So brains instantiate minds in the same way that computers instantiate computer software. The things that we do with this hunk of meat are the functions that specify how we behave, basically. And the functions that specify how we behave are the very essence of mentality. So the analogy between the mind and a computer program is held to be very strong and maybe even identical by the machine functionalist or the computational functionalist. So for the really hardcore computational functionalist, there might be a kind of way to specify how I am programmed that then specifies everything about my mental states. And if you were able to find this programming language that my mind software is written in, you'd be able to identify everything about my psychology. That's sort of one extreme version of machine functionalism. And we'll look at some other specific dimensions with this next time when we talk about the sense in which machine functionalism requires a particular kind of symbol system and a particular kind of mental language, a mentalese, if you will, and whether that's necessary or not for machine functionalism and all of that good stuff. For today, we're just going to be focusing on the definitions of these views and problems that crop up with these two related views, machine functionalism on the one hand and functionalism more broadly on the other hand. So for today, I had you all read the first chapter of Andy Clark's Mindware, An Introduction to the Philosophy of Cognitive Science, which is, I think, a really lively and provocative introduction to the philosophy of cognitive science. And you might find yourself disagreeing with Andy Clark on some of the things he says. One important thing to note is that not all cognitive scientists are computationalists like Andy Clark. A bunch of them have stopped subscribing to that view, and that might be something that comes up in our discussion this week and next week as we continue to talk about functionalism. So let's talk about the basics for a second. I have a short presentation for you here today to just go over the basics of machine functionalism. This first slide shows a kind of Turing machine that someone tried to build, and we'll talk about Turing machines more in a second. So this is here a picture of Alan Turing, who was a famous computer scientist, logician, formal developer of cryptography, a lot of other stuff. He was a cool guy, very smart, kind of a tragic end to his life. And the UK has formally apologized to Alan Turing in recent years for the pressure that they put him under for being gay. He was gay and committed suicide, people think, because of the pressure from the British government. Nowadays, he's considered a hero to the British Empire, and he's been recognized. So good for Alan Turing. You might have seen a movie featuring this guy in recent years. He's been played by Benedict Cumberbatch, which, you know, makes sense. They're both handsome people. All right, so Turing, insofar as he's related to the question of AI that we'll be talking about today, suggested that rather than asking whether machines can think, which was a pressing question, believe it or not, even in the 40s, you know, people could see far into the future. They could see that machines were going to change the world, and they were already curious about whether or not it would be possible to program a machine that could think. Turing said, let's replace that question, can machines think, with something that he wanted to call the imitation game. Nowadays, we tend to call this the Turing test. The imitation game involves a human volunteer, an AI, and a judge. The judge has to guess which of the chats he's having is the chat with an AI. And if an AI can pass the imitation game or win the imitation game, Turing says that AI is as good as intelligent. We should call it an intelligent computer. Now, we might ask the question, does it make sense to replace the question, can machines think, with the question, can a judge guess the difference between an AI and a person? And I pose this question to you, and I'd love to hear what your thoughts are about it. Quick side note, this picture here is a picture of Kismet. He's a robot that you can find in the MIT Museum of Computing and Robotics. And he was one of the first robots that was made that could have emotional expressions on his face, which is why he's got these eyebrows and these ears and a mouth. Kind of cute. So here we have a definition of functionalism again. And functional states, right, are understood to be functional states like in a machine. They connect input and output, sometimes by way of other functional states. And machine state functionalism is a specific kind of functionalism and a specific kind of computational functionalism, according to which any creature with a mind can be regarded as a Turing machine. And a Turing machine is an idealized finite state digital computer whose operation can be fully specified by a set of instructions called a machine table or a program. And they each have the following form, that if a machine is in a particular state, call it Si, and it receives a particular input, call it Ij, it will go into another state, call it Sk, and produce output O1, for example, for a finite number of states, inputs, and outputs. So this here is an example of a very simple kind of Turing machine or a finite state machine. The tape here, it carries information in the form of zeros and ones, a kind of binary code. This machine head reads the tape and writes on the tape. Those are the only two things it can do. And this little machine instantiates a program that can supposedly describe just about any computation that you can do mathematically. And so something that is computable is defined by Turing. And so anything that's computable can be computed by this little Turing machine. So the idea of machine state functionalism is that any creature with a mind can be regarded as a Turing machine or can be specified by a set of instructions that a Turing machine could follow. Of course, the finite state machine, like the Turing machine, would be much slower at doing whatever it is that the creature with a mind can do in ordinary circumstances, but functionally speaking, it would be able to do the same thing if we just look at the input-output relationships. So it's kind of an extreme claim. It's sort of surprising to hear that something as simple as this is supposed to be able to do just about anything that you can imagine that a creature with mental states can do. That is the claim of machine state functionalism. Now, do we agree with machine state functionalism? Not so much anymore, largely because people, including Andy Clark, right, think that the way that we specify the functions might determine what kinds of physical states can instantiate those functions, and so we don't totally throw brains away altogether in modern computationalism, but it is the case that there's something about this specification that is abstract enough that that is appealing, right? The idea is mindware is software, and nowhere is that better captured than this definition of machine state functionalism. So here's an example case you're curious about what functions are supposed to be or what they look like and you're still confused, here's an example of a kind of functional map of a vending machine. So a vending machine has several functions that it can instantiate depending on what you interact with it, what you do, right? So its basic state is it's idle, it's just waiting. It's kind of its default state. If you insert a coin, it will count the number of coins it has. If it doesn't have enough coins, then it will output give change or something. It'll reject the coins. It'll cancel the function. But if enough coins are inserted, then it will maybe display an option for you to select a soda, for example. And then if you press a button to select a soda, right, then it'll dispense a soda. And once it's dispensed the soda, it automatically perhaps moves over to the give change function. And then once it's done that, it moves back to being idle. This is a really, really simple kind of functional table, kind of like a depiction of what a functional table would enact. And these circles here represent each of these functional states that the vending machine can be in. And the transitions between these states are specifications of input and output relationships, right? So enough coins here is the situation that gets the machine to move from its count coins state to its select soda state. So the idea is like every single mental state can be described in this way, where it's like a select soda condition or it's like a give change condition. You can place it in a relationship with other mental states and other kinds of physical input and output that say everything there is to say about that mental state. Now, remember, machine state functionalism doesn't necessarily say that every single machine state, like specifiable machine, right, is therefore a mind. So it's not necessarily the case that this vending machine has mental states. It's just that something with mental states can be described functionally in such a way that it can be instantiated by more than just something with a brain. So here's a simple functional specification of things that we do think have mental states. A dog, right? And here's a robot dog. Machine state functionalism, computationalism allow that either kind of creature could potentially have a mind. So here's a functional specification for a very simple dog program. And here's a cat, grumpy cat specifically. And you might think that you can specify grumpy cat functionally as well, although there's a very simple function here for this cat. So basically, if dogs and cats were finite state machines, they would have functional specifications that you could give that would look maybe a little bit like this. Okay, so according to Turing, all computation could in the end be done with an infinite state Turing machine. If this tape was infinitely long, this Turing machine could compute anything that you can compute. And Turing machines are really simple, right? They just have an input, they have a controller, and they have a memory store and a way to output responses. And that's it. Of course, you can contest multiple machine states into one state if they ultimately produce the same behavior, and this saves computational time and storage space. This is called state minimization. It is useful for designing finite state machines or FSMs like vending machines or coffee dispensers. So you want to produce, when you're making robots and stuff, you want to produce the most minimal specification of something so that it can produce the sophisticated behavior you want. State minimization can be a more efficient way of programming things that you want to program. So it looks like you'd be able to model a really complicated organism with very simple functional specifications and still get a pretty high fidelity input-output match if you can do enough of this state minimization. So there would be lots of ways actually to instantiate something with a mind if you thought that mindware is software. So what this enables is multiple realizability. Again, the biggest advantage of functionalism is that it allows that mental states could be multiply realizable. There are many physical realizers that can produce the same functional states, so there are many ways of producing mental states. So you might get mental states made up of brain stuff, mental states in something with a robotic mind, a robotic hardware, and mental states coming from something with alien hardware, right? All of that would be a way to build a mind. So well, Professor O, what kind of importance does machine functionalism have for us? Why would anyone be a machine functionalist and not just like a broader kind of functionalist? What's that distinction about? One reason is that, you know, the analogy between minds and software is really compelling to some people. You know, the very idea behind artificial intelligence is that we might be able to program a mind into existence. We might be able to make new sentient beings out of computational hardware and software. Now, if you're interested in artificial intelligence, it's important to distinguish two theses that you might have. One thesis, call it strong AI, is the thesis that computers could one day come to truly understand language, truly have mental states, etc. Maybe you think if strong AI is true, robots could even be conscious one day. Maybe something like this will one day have conscious experiences, or whatever she's connected to would have conscious experiences, and she'd have a really strange mental life. And some of that has already been explored in movies and TV, right? We love imagining what it would be to live in a world with genuine artificial intelligences. So that's strong AI. If you think that's possible, then you're a proponent of strong AI. And that kind of goes along with the theory that computationalism is true, right? Why not say that the reason that there are artificially intelligent beings possible is because minds are just software? Now, another thesis that you could be a proponent of that's not quite as all-encompassing as strong AI, call this weak AI. That's the thesis that computers could successfully imitate or mimic human behavior, such as language behavior, but not necessarily would that mimicking or imitating amount to truly understanding language or truly having mental states. So right now, it seems like a lot of our sophisticated technology, a lot of our sophisticated artificial intelligence genuinely can mimic language pretty well. I might even be able to have a conversation with this little being right here. Computer, tell me a joke.
What does Frankenstein drive?
I don't know what.
A monster truck.
See, and it can respond to requests to do things. I might be able to order toothpaste through this device. I haven't tried to do that. I can turn lights on and off with this device. Not in this room. I don't really have any high-tech stuff here. But artificial intelligence has slowly enabled us to do lots of stuff we couldn't do as easily before. Lots of stuff that might require typing, but now I can use my voice. So it's clear that like artificial intelligence is able to slowly start to understand human language, even spoken language, perform translations, do lookups on the web, buy items for us, move our lights. But even though all of those things are quite intelligent things to do, you might be left wondering whether this being, whatever it is actually sentient or whether it's just mimicking words that we say. You know, the way that a parrot might repeat things that it's heard, just in a kind of extra way. You know, Amazon has the big bucks for making something like this. So if you think that artificial intelligence could only ever hope to mimic our language, then you're a proponent of weak AI. If you think that one day computers could genuinely come to understand language, genuinely feel emotions, genuinely have conscious experiences, then you're a proponent of strong AI. So speaking about functionalism more broadly, according to a functionalist, what makes a system be an intelligent system or even a sentient system has something to do with what it has a capacity to do, what it is disposed to do in response to things that happen to it. It is the capacity to do things that makes it intelligent, not, what it is made of. So it doesn't matter whether or not you're made of a brain or of ectoplasm or silicone chips or electric currents or hydrogen atoms, whatever it is that you're made out of. What matters more to whether you're intelligent or not is what you're capable of doing. So what makes a particular system be a system that can understand words, for example, is a matter of its causal profile, right? And what makes a system an intentional system, for example, a system capable of understanding meanings of symbols and language, is a matter of its causal history, according to many of these functionalist views. Now, one question you might ask is, why would we want to treat thought in this way, as functionally specifiable? Multiple realizability is one big draw for lots of functionalists. We like the idea that maybe minds can be modeled in more than one object. It seems possible for intelligent behavior to arise from more than one kind of entity. Maybe brains aren't so important. Maybe it matters more what brains are allowing us to do, and computationalism might be a way of explaining that. If our brains are capable of instantiating a meat program that produces conscious experiences because of the information that it's processing, then we'd have some insight into what it is that makes brains a little bit special, because something about neurons is important to information processing. And it turns out that neurons aren't the only things that can process information. And so if we can build other things that can process information, then those things might also have mental states, right? And that's the attraction of computational functionalism specifically. Using the software analogy gets us some powerful tools for trying to explain, model, and map out human behavior and human dispositions, and also to explain and map out intelligent behavior for non-human creatures, including robots, maybe aliens, and maybe other kinds of beings that have yet to be explored or discovered. Maybe there are things in our natural environment that have computational specifications that we haven't explored yet. So maybe there are things with minds that don't have brains out there in our world that we haven't thought about that much yet. So in response to the question, why treat thought as computation? Andy Clark says, and I quote, "Thinkers are physical devices whose behavior patterns are reason respecting. Thinkers act in ways that are usefully understood as sensitively guided by reasons, ideas, and beliefs. Electronic computing devices show us one way in which this strange dual profile of physical substance and reason-respecting behavior can actually come about," unquote. So he's saying that one reason to think of thought as computation is that because computation can be specified in a way that's abstracted away from its physical specification, you can understand something as a computer without understanding the hardware, right? That is a way of actually getting a different type of explanation of behavior when you think about minds. So his example is, if someone has an accident and you pull out your phone and you dial 911, there's a physical description of that causal set of affairs, right? The light that came into my retina from the person who collapsed in front of me, and the way that that triggered certain neural activity, and the way that that triggered a certain motor activity with me pressing buttons on my phone, and then dialing 911, right? You can specify it at that level of description, which is a purely physical causal level of description, but you'd be leaving out an important sense in which I'm actually reasoning about the situation in front of me. So another kind of explanatory causal depiction you could give of this situation is as of me having a particular mental state, which is a desire to help the person in front of me. And because of my having that desire, I take out my phone and I dial 911, which is the emergency number here in the United States, and not, for example, 999, which is the emergency number in the UK. If I were in the UK, I would have dialed a different number. And explaining why I dialed 911 is easier in a sense to do, given that I'm thinking at this computational or reason-guided level of explanation, as opposed to the purely physical fundamental level of specifying the causal relationships. There's a sense in which the physical level, the fundamental physical level, wouldn't be able to explain why I dialed 911 instead of 999. It'd be good at answering different kinds of questions, like why I pressed in this spot instead of that spot. But basically, you get different explanations from different levels of explanation, and the computationalist thinks that the level of explanation that they can give is very helpful for understanding mentality. According to the computationalist as well, such a behavior explanation might also require postulating that I have things that are internal symbols or internal representations of my environment. And the computationalist thinks that these symbols are the things that I manipulate in order to be able to do my reasoning, in the same way that a computer uses symbols in its programming and manipulates them and puts them in causal relationships and can do different kinds of processing in order to be able to respond to queries and solve problems. Now, one major objection that we'll talk about today, and we'll leave the language questions and the representation questions for next time. One of the major questions we'll talk about today is whether mimicking or modeling intelligent behavior might be sufficient or not for instantiating mentality. That's one of the major objections to computational functionalism, and sometimes to functionalism more broadly. So it's possible, right, to simulate a rainstorm without anything getting wet. And so that suggests that simulations aren't the same as the real thing. And so the fact that I could simulate the input-output relationships that might be instantiated by something with a mind by writing a computer program, or like a chatbot, the fact that I can program a chatbot to have a human-like conversation doesn't necessarily mean that the chatbot can understand language in the same way that a human can understand language. It's just imitating or mimicking what the human is doing in conversation without actually grasping what the human is doing in conversation. Same thing as the rainstorm. Simulating a rainstorm, but nothing gets wet. I can simulate language use without anything being understood, right? That's the objection. Are simulations sufficient for intelligent behavior? Andy Clark's response is that you might be able to produce intelligent behavior that is sufficient for mentality without necessarily producing intelligent human behavior or intelligent human mentality, right? So there's two ways to fail the test of intelligence. One way to fail the test of intelligence is not to actually produce anything intelligent. The other way of failing on the test is to produce something intelligent, but that's not intelligent in a human way. And Clark is of the position that we might have already made artificially intelligent beings that are intelligent and potentially, maybe, possibly sentient, but that are not thinkers in a way that we traditionally would understand as thinkers. They're thinkers in a kind of alien way, in a new way. They think in very, very different ways than we do. And that makes it sort of hard to think about. If you think about IBM's Watson machine, which they built and ran against some real human players, and it beat these real human players at a game of Jeopardy in 2011, which was thought to be really, really difficult at the time. And we still think it's difficult, but it's quite a sophisticated thing to do because Jeopardy involves wordplay, it involves like having a large database of knowledge and a lot of other stuff that computers were still trying to get good at the time. But it's now been 9 years, and so that hurdle has been jumped. Maybe you think Watson has mental states and they're genuine mental states. It's just that Watson, whatever way Watson works, is not like the way that a human works. The Watson's way of playing Jeopardy was a little unusual, and if you want to watch a clip of that, I'll link to it for you on our website. What Andy Clark says is that it's true, you know, like a simulated rainstorm doesn't make anything wet. It's unclear whether the Turing test tests for human intelligence or not. Maybe it's too behavioristically superficial, but whether simulated intelligence is intelligence depends on what kind of thing intelligence is. If intelligence and consciousness are informational phenomena, then simulation may well be enough, because all that you'd need is to replicate the informational phenomena. And programming is a plenty good way to do informational processing, right? So distinguish informational processing from something like delivering a pizza. If you order a pizza and you just get the picture of a pizza, you'd be pretty upset, says Andy Clark. When you want a pizza, you don't just want a simulation, because being a pizza is essential to the operation. But if the essence of intelligence is informational, then maybe whether or not there are pizzas, or in this case, brains, doesn't matter so much. However, if there's something about the chemical profile of things with brains that is essential to their capacity to be intelligent, or their capacity to be sentient, or their capacity to have conscious experiences, like if the minute chemicals or hormones that are swimming around in my brain are important for the kinds of operations that I do that are mental operations, and not just important in an informational way, but important in a deeper way, like the pizza way, then functionalism will turn out to be false, because there will be a specific structural specification of intelligence or of consciousness or whatever other mental property you want to talk about that can't be instantiated purely informationally. And so you won't be able to simulate a human mind without having a physical brain. You'd only, well, that is, simulating a human mind without using a brain would be mere simulation, as opposed to actual reinstantiation or actual exemplification of having mentality of a human kind, if that makes sense. But maybe there's more than one way to be intelligent, and maybe there's more than one way to be conscious. And if there are more than one set of chemicals that can produce beings with conscious experiences, then probably something like a functionalist view would have to be the explanation. So that's all I have for today. We've crossed a lot of territory. The main points that I want you to remember are, first of all, the understanding of causal functionalism as a type identity, which is a rival to the type identity for mind-brain identity theory. And second of all, that machine functionalism or computationalism are kinds of functionalism. There are functionalists out there that are not computationalists. And we haven't talked about what it is that makes the, call it the causal theoretical functionalist, different from the machine functionalist. But broadly speaking, it's something like, there's something wrong about the analogy between software and mindware. Maybe there's something about the requirement that we have symbols that we can describe as being inside the mind, you know, like in here, that you could model those, that there's a language of thought, that the mind is a programmed thing, you know, we have a programming that is specified by the way our brain is structured or something. People who don't like computationalism often just really hate that metaphor for mentality. And there's a way to be a non-computationalist while still being a functionalist, still thinking that mental states are things that have functional profiles. They're dispositions to react to the world in particular ways, without necessarily saying that the dispositions must be able to be specified in a computational way, or in terms of a finite state machine, for example, if you're that kind of machine functionalist. So once again, functionalism is a broad family of views. computational functionalism is kind of one of the sets of views you could have that fall within functionalism. And their main distinguishing feature is that they see mental states as identical to functional states. Mental state types are identical to functional state types. And then the key is, well, what sorts of functional state types? And that's what we'll be talking about. So next time, we'll talk about symbol systems and the idea of a language of thought and what computational functionalists think about mental representations. So stay tuned and thank you for tuning in. See you soon.